So we're very happy to have you, Zhao, from MIT, who will tell us about a weak quantum toroidal categorification on Hilbert schemes.
Yeah, thank you for the invitation. Actually, as on Monday, because I'm in our seminar for several weeks, and I'm trying to check the schedule for who is giving the talk this week, and I realized that it's myself. Okay, so today I'm talking about a weak quantum toroidal categorification on Hilbert schemes. And first, let's make an overview about what we will talk today. So the quantum toroidal algebra could act on the Grothendieck groups of the Hilbert schemes of points on surfaces. And this action generalized the Heisenberg algebra action on cohomology, and this is the very famous result by Nakajima and Gorenstein. And today our talk will be one more step in trying to obtain a weak categorification for this action on the Grothendieck groups. So okay, so what's quantum toroidal algebra and what's the Grothendieck groups of Hilbert schemes of point? So here we have, I mean we are always considering a quasi projective smooth surface, yes. And I think for representation series, they would care more about the case that the surface is A2 or some quadruplet resolution of type ADE singularities. And here we consider the Hilbert scheme of endpoints on surface on S, and we consider the union as the modular space. And the famous results of the Nakajima and Gorenstein explain that the homology group actually could be regarded as the reducible highest weight representation of the Heisenberg superalgebra. So here the Heisenberg superalgebra would involve part of the Heisenberg algebra part, and also a part of Clifford algebra. Associated to the cohomology ring of X, and here actually as S over here, and the highest weight vector is the case of 0 point, so the cohomology is actually Q. And let me make a remark here. So when the surface is A2 itself, what's homology group would be? It actually should be the it actually should be the polynomial of the symmetric polynomial of infinite variables, and this Heisenberg algebra action is actually what we know the focal representation. So here we review the case of homology group on the Hilbert scheme points on surfaces, and then for algebra geometers, we will care about how, when we change the Hilbert homology to the algebraic K-theory, what will happen? And this is obtained by Schiffer, Mossrot, Figgins, Beliuk, and Andre, and they constructed a quantum toroidal algebra action on the Grothendieck groups of Hilbert scheme of points. So first, let me explain what's the quantum toroidal algebra. So when we change homology to Grothendieck group in general, we need to make a Q deformation, and so for the case of Heisenberg algebra, we will deform it into Q Heisenberg algebra. And here the quantum toroidal algebra is actually an finalization of the Q Heisenberg algebra. And as we have said here, so today we will talk about the quantum toroidal algebra through the viewpoint of algebra geometry, but we can also consider this through the viewpoint of representation theory and also algebraic combinatorics. For example, like the shuffle theorem. And the definition of the quantum toroidal algebra is listed over here. So we consider the Laurent polynomials which are symmetric, and the quantum toroidal algebra actually are generated by by the generators EK, which is in the positive part, the FK, which is in the negative part, and there will also be a relation. There will also be some zeros part, which is HL plus and minus, and their relations are.
Sorry, can I ask before you move on?
Of course.
What is the subscript here? K, yeah, parentheses, you have square brackets 1, square brackets 2.
Which one, EKFK?
No, the third bullet point, let K be.
Oh, so I think because here we are actually introduced some kind of integral version for the original definition of quantum toroidal algebra, we are consider the functional field of two variables Q, QT, right? Yeah, I mean because quantum
I'm trying to ask what is the subscript? What is the meaning of the subscript?
It's localization, Matt. You want to have divided powers, right?
Yes. So can you repeat your question?
You know that, but I think I was answering to Matt. I think you want to have divided powers, so that's what you're dividing by, the 1 divided power, 2 divided power, 3 divided, right? The factorials.
Sorry, you are asking 1, 2, 3.
Yes. Yes.
Sorry, I think it's my mistake. I mean, K is just the symmetrical Laurent polynomial. So I think wait for me.
Okay, thank you.
That should not be there at all.
Yeah. Yes.
Okay.
That's yeah.
Okay, thank you.
Oh, I see the point, because here we are considering the integral version. So actually I think here 1, 2, 3 means anyway. I think it should just be a mistake over here.
Okay.
Yeah. So, but I want to make a remark here. So we are actually considering the symmetrical part. So we are always consider like Q1 plus Q2 and the Q equals to Q1, Q2, but not a single Q1 and a single Q2 action. The reason is that I mean, for the case of A2 with C-star action, we can always, I mean, 2 C-star action, we can always consider Q1 and Q2. But for general algebra surfaces, it doesn't make sense to define the to define the two roots, two chain roots Q1 and Q2. But their sum and their product have geometric meanings. Okay. So the relations are given over here, and the first one is positive part. The second one is explain the relation between positive and the zeroth part, and there is the third one, which is the star relation in the situation, and the last one explains the relation between the positive and the negative part. So any question right here, right now? Okay, great. So let's explain how this acts on the Grothendieck over Hilbert scheme points. And I want to make a remark here for the case of surface equal to A2. I mean, the case because the Grothendieck group of all Hilbert scheme points actually will still be the focal implementation, but over the ring of Q functional field Q1, Q2. So actually in the case A2 we can define this algebraically, but for general surfaces we will need some geometric notion, and also the geometric definition. I mean, red looks more elegant. So let's explain what happened for the for the Grothendieck group case. And here, I mean, we already defined Hilbert scheme, and we now will need to define one concept, the nasty Hilbert scheme, which is parameterized by two ideals such that their difference is only 1 point. And because their difference is only 1 point, there would be a unique tautological line bound on the nasty Hilbert scheme, whose fiber over a closed point would be the quotient of this two ideal sheaf. And okay, we define this lie bundle, and we could regard this lie bundle as as correspondences from the Hilbert scheme points to the Hilbert scheme points times S. So here, EK and FK looks like the same, but the difference that EK mapping the Grothendieck group of Sn to Grothendieck group of Sn plus 1, and the FK maps the Grothendieck group of n plus 1 to the Grothendieck group of Sn. And here I want to make one more remark about what's Q1, Q2 over here. So here, because remember that the operator is associated to the Grothendieck group of service itself, and in this situation, the Q1 plus Q2 would be the cotangent bundle of the surface, and the Q1, Q2 would be the canonical bundle of surface. So actually, we could regard Q1 and Q2 as the turn root of surface, but we couldn't define turn root as an element of Grothendieck group. So this is a reason that why Q1 plus Q2 and Q1, Q2 appears over here. Any question? Okay, so now let's talk about, so how the Grothendieck group action. So here we know that, we know that there are, there are operators HM mapping the Grothendieck group of Sn to Grothendieck group of Sn itself, which is a combination of the symmetric product and batch product of the universal ideal shifts, such that the commutator is just HK plus L divided by 1 minus Q, and the delta diagonal mapping, and moreover we can prove that the operators EK, FK, and HL satisfy the relation in the quantum toroidal algebra. So from now we know that the quantum toroidal algebra could act on the Grothendieck group of any algebraic surfaces. Okay, any question? Okay, so let's talk about our topic today. We will talk about a weak categorification of the quantum toroidal algebra. So how do we mean the weak categorification? So actually, as I have said for the quantum toroidal, there are several parts of the relation, and the positive part of this quantum toroidal algebra is already categorized, in a big sense by Andrew in his paper several years ago. And there is also another monoidal categorification of the positive part, which is given by Morapota and Francis Salas through what they call the two-dimensional categorified whole algebra, and they are doing this through the way of the derived algebra geometry. And today, for our categorification, we are consider the commutator of a positive part and the negative part, and we want writing this commutators through explicit natural transformations in the derived categories of Hilbert scheme of points. So this is our purpose for this talk. And what we prove is that okay, so
can I interrupt you?
Okay.
Before you're going to tell us how to categorify the HK plus L, so you're going to tell us also how to sort of simultaneously categorify the positive and the negative part, which neither Negut nor Portesella have done. Is that correct?
Huh? Oh, for the no, because as I have said, actually, Andrew only did the positive part in weak sense, and the Porter and Stella, they are doing this through the framework of Shipman and Westeros, through what we call the cohomology whole algebra or categorified whole algebra, and this one could only deal with the positive part.
Yeah, that's what I mean. So you before you categorify the commutator, you actually are going to bring in something new, which is you're going to categorify both the positive and the negative part. Right?
Yes.
Yeah. Okay.
So this is the reason that we could mix this make sense for a categorification, a weak categorification of the whole quantum toroidal algebra.
Okay. All right. Thank you.
Yeah. And thank you so much for your comment. So what so what we proved here, I mean, contains several parts. First, we know that I mean there do have natural transformation. I mean very I mean they do have explicit natural transformations from the operators f and e, and it depends on m is the positive, negative, and zero. I mean the direction would change, and moreover for the case m equals to 0. It is a decomposition that f minus r er would be the same as er f minus r. Direct the diagonal shifted by 1. So this gives this gives actually a geometric proof about the Hilbert classification given by Anthony Carter and Singularities. And the second one is that, okay, we consider the cone of this one, and we show that there are natural I mean, this cone have filtrations. I mean, has filtrations, and the associated gradient product is also combinations of that symmetric product of universal shifts on the m times s. And the third, we show that at the Gorenstein group, it matches with the computation we have over here. And finally, we want to say that different from the case m equal to 0, it is direct sum. The extensions, I mean, the extensions for the positive and for the m positive or m negative part would be non-trivial, and we gave a explicit formula about the extension class also in our paper. So this is the
Can you go back one slide?
Okay.
Thank you. So I'm a little not confused, but so in your first statement, can you remind us actually what is the positive and what is the negative part? Because
the positive part would be EK.
And the negative part is
FK, FJ maybe.
So I'm confused. I mean, not confused, but when you say that there's a natural transformation, you're already assuming that both EK and FR have been categorified.
I mean, because EK and FR can be naturally categorized as a line bundle on the next cubes of points. Yes, you are right. EK could be naturally categorized because here we given EK as correspondences of some line bundles, and if we regard this as the Fourier-Mackay transform, it given categorization of EK.
And then I'm sorry, I'm confused about the statement you made about Andres having only categorified the positive part. So it seems like what you wrote before. It seems that there are already candidates for categorifying, maybe in a weak sense, both EK and FL, correct?
I mean, the issue that we could categorize this operator, but we don't categorize the commutator. So for a weak categorification, we should not only categorize the operator, but we should also need to understand how to write the commutation in the natural transformations.
I see. Okay.
So for example, I mean, for the relation 3, the cell relation, how do we written this as the explicit derived category, and is through the explicit natural transformations.
Mm-hmm. I see.
Yeah. So this is what Andrew did in his paper, high correspondences for modular space of shifts.
I see. So to summarize, and I'm sorry, I'm just being slow at understanding. You've actually already said everything correctly. It's just I'm processing very slowly.
I mean, no, sorry. I think maybe I just said it too fast.
No. But so just to summarize, the situation is that there were, prior to your work, there were already candidates for categorifying both EK and FL. But what categorifying is not EK and FL, but rather the relation that holds them with that define. Okay, defining natural transformation and so on. Okay.
Thank you. It's totally right. And thank you so much for your comment. So okay, so let me make 2 more comments over here. So first, I want to say that this is only a weak categorification, we have not studied the maps between the shifts and the relation between those morphisms. We have not studied this very clearly, and we need to know how to do this in the future. And another thing that we could also consider this kind of case, because quantum toroidal actually could also act on the higher rank of stable shifts on the on an algebra surface, and we could also consider classification of action for the higher rank stable shifts. But there is some difference from what we introduced here and this setting. And I just want to say one more word why this question is interesting, because if we because for the higher rank case, we know that the quantum toroidal algebra action actually would factor through some W algebra action, deformed W algebra action, and this gives an proof of the AGT conjecture. Okay, so now let's talk about the proof of
Oh, sorry, and you're saying so you expect that you should be able to upgrade it from the weak categorification?
So the first one is that we want to update from the weak to the strong sense, to the two classification sense. Okay. Yeah, okay. But here it is only a classification in the weak sense. But actually we have some projects about how to update this to the strong sense.
In the sense of the two categories.
Yes.
Okay. Okay. Thank you.
Thank you so much. Okay. So let's talk about the proof. So first before consider proof, I mean we remember that EK and FL are categorized through the Fourier chi transform. So we need to understand what the EKFL and FL EK really looks like in the Fourier chi transform. So here, I mean, other than the Nancy Hilbert scheme and Hilbert scheme, we should define several more modular space. So here, first we introduce the quadruple modular space, the triple modular space, Z plus and Z minus. The left side Z plus and the right side Z minus. The parameterize the diagram such that the ideal shift IN plus one is including in two different two ideal shifts which might be different or the same IN and IN prime, and their quotient will be the point X and another point Y. And we could also consider this for the decreasing side, which we have two ideal shift IN and IN prime, but they are both including another ideal shift IN minus one. So here, here I want to make some notice, remember their quotient is spotty in some points, and now we define the quadruple modular space Y. So here, actually, it is more like a combination of the two modular space, but we want to make one more requirement such that IN minus one quotient IN prime is same as IN quotient IN plus one. So is IN minus one quotient IN and IN prime quotient IN plus one. And here we could moreover define several line bundles L1, L2, L1 prime, L2 prime, just like what we did for the Nancy Hilbert schemes, and they corresponding to line bundles with fibers of this point respectively. And so the relation of Z plus Z minus and Y is given by this Cartesian diagram. We could always mapping Z plus to Sn times Sn times S times S by remembering the IN prime and the point X and Y. So it gives us a Cartesian diagram. But I want to make a remark here. This one is a Cartesian. This one is a fiber product, only in the sense of scheme case, but not in the sense of derived scheme. Yeah, it would be important if we want to enhances to some DG level. And here we wanna, do some basic understanding about the geometry over here. So actually we know that the plus, the minus is irreducible, but the plus would have two irreducible components. One corresponding to that IN and IN prime are the same. So this is W1, which is exactly the next Hilbert scheme. And another one would be the case that IN and IN prime would be different. In this case, W0 would be the image of alpha plus in this sense. So, and we know that W0 intersect W1 is also an exceptional divisor of the next Hilbert scheme. And okay, now we want to understand what's the geometry property of W0, W1 in minus and Y. We know, Andrew proved that Y is smooth, and we know that W0, W1, the minus are Gorenstein of the same dimension, and they are the expected dimension. And moreover, we know that alpha minus and alpha plus are bidirectional to its image. And because W0, W1, A minus are Gorenstein of the same dimension, so actually the Fourier chi transform would coincide with structure shift. So we know that EKFM is exactly push forward of the, FM and EK are exactly the push forward of the line bundles on the plus and the minus. Any question? Okay, great. So because of that, remember that what we need to do is that we need to compare EK and FM. So one side is the line bundles on the minus, and another side is the line bundles on the plus. So we need to do two comparison. First, that to comparison the plus, the minus, and the Y. So actually, what we need to do is that we need to prove that the minus and W0, which we have remember, which is the one reduced components of the plus, they are actually rational singularities. So here we mean that the push forward of structure shift for it, so it push forward the structure shift to structure shift, and the hard direct image would vanishing. So this is the first comparison we need to build. The second comparison build is that as we have said that we could define L1, L1 prime, L2, L2 prime. All those line bundles to be defined on Y, and we want to compare those line bundles on Y. So this is the second part we need to do. Actually, the second part also has been built by Andrew by this one. And so recall that okay, we consider Y as full ideal shift, and we could always make that IN equal to IN prime. Then this closed-up scheme is actually the negative scheme of n-1 and n+1 point. So moreover, here we require that the two quotients of ideals are actually supported in the same point. And this one is the regular codimensional one closed-up scheme of the quadruple modulus with Y. And moreover, what we have that we know, we know that L1, L2 prime inverse equal to L1 prime, L2 inverse, which is the categorical divisor of this regular codimensional one subscheme. So here we built we built the second part of the comparison of line bundles on the plus and the comparison of line bundles on the minus. So any question right now? Okay, great. And actually, yeah, actually those so you said those comparisons has also been done by Andrew for the weak categorification of the positive part. So this part in some sense is not the most difficult part, but the difficult part would be the geometry. How to prove that the plus and the minus has the expected singularity we need. For the, and so this problem would also appear for the case of a positive part, but it would be much easier for the positive part because for the positive part, the preimage of alpha plus and alpha minus could either be 1 point or a P1. So generically they are so the dimension of fibers would never be more than 2. So we know that by the Grothendieck convention theorem, we know that the higher image for I greater or equal to 2, it always mentioned anyway, only need to deal with the R1 case. But this, and sorry, yeah, but this totally doesn't work for the case of positive and negative part. As for the positive and the negative part, the fiber could be arbitrary dimension, and we couldn't control. We couldn't control the fiber and use the Grothendieck convention to do all this stuff. So the approach for the positive part doesn't work for the commutator relation of positive and negative part. So how do we deal with this geometry picture? In order to do this, we need to actually use some singularity theory of the minimal model program. And the key concept here is what the birational geometers call the discrepancy. So let me first ask question: do we have birational geometers in our talk today? Okay, great. So I just wanna make a remark for birational geometers because for birational geometers actually they usually work in the Q the Q divisor case. So actually they are always assuming someone is Q Cartier instead of Cartier. But here, as today what we will deal with are all Gorenstein schemes, and in this case the canonical divisor is Cartier. So we would only consider discrepancy for the integral version. So what's the definition of discrepancy? So now assume that we have a Gorenstein variety and we have a resolution f from y to x, such that of course y is smooth and the map is birational, and we can consider the exceptional set, which we mean that on y, which we mean that f is not an isomorphism. And there would be the exceptional divisors EI supported in those exceptional sets, and there would be integers AEIX such that the canonical divisors are different by those exceptional divisors, and we call this AEIX the discrepancy of EI with respect to X. And and in general, so from the viewpoint of birational geometers, they regard the discrepancy and as some sense of the how good the singularity would be, and actually if the number AEIX is larger, the singularity is better, and if the AEIX is smaller, the singularity is worse, or what we say is more wild. And there are also some classifications such that if all the so here, as I mentioned, so here we define the notion of canonical singularity if all AEIX is non-negative, and we could also say that it is a low canonical singularity for AEIX greater or equal to -1. And there are also other notions like KL Kawamata local terminal local singularity, or divisorial log singularity, log terminal singularity, and other singularity, but we would not introduce today. We would focus on canonical singularity. What's the advantage of canonical singularity is that if it is a canonical singularity, then it is a rational singularity. So we could push forward the structure shift to the structure shift. And for the case of Gorenstein right case, the other side is also true. If X is Gorenstein and it is autorational, actually it would be a canonical singularity. So the other side also holds. So our main theorem over here is that okay, we have alpha minus alpha prime, and what's alpha plus? What's the exceptional divisor? The exceptional divisor could only be the delta y we have defined over here. This part is trivial, but the non-trivial part is that we show that the discrepancy of this part, of those two morphisms are 1 and 0 respectively. So because 1 and 0 are both non-negative, we show that this one, these two varieties are really canonical singularities. So any question right now? Okay, great. So let me make some brief explanation about how to do the proof. The proof of the discrepancy over here. The part of alpha plus is kind of easy because actually it is isomorphism outside of codimensional 3 locus on Y, and we know that in this case it is I mean the discrepancy would be 0, and a bit harder part would be the alpha minus from Y to the minus, and actually this one is to prove this one we should look at some local some local part of this geometry, and we could see that for some open set this morphism is actually it looks like that S times S blowing up the diagonal, and because it is blowing up a codimensional 2 locus with the codimensional 2 scheme, we could see that the discrepancy would be 1. And I should say that when we blow up a regular codimensional K scheme, we know that the discrepancy would always be K minus 1. Okay, so any question over here? So yeah, so based on the so now we have built on the two main tools for proving the classification. We already built the comparison theorem for line bundles. We also built the comparison theorem for the varieties. So now I wanna show how to integrate them to give a weak classification. And the case of HK part would be would involve a lot of computations, and I have no plan to show it over here. But I want to make an example for the H0 case. So we want to show that f minus 1 is really ER f minus 1 direct sum of delta 1. So okay, so how do we do that? So first we compute the ER f minus R, as we have said it is line bundles of push forward line bundles on the minus, and as alpha minus are rational singularities, it is the push forward the line bundles on Y, and also we could use the another side of the diagram and first given this formula. But this formula is not good enough. Actually, we want to show that we want to remove the part of R alpha plus star O minus delta Y, and we want to replace this by just the structure sheaf of the class. And for here, and in order to do this, we need some computation. So okay, first on Y we have showing that sequence. Of coherent sheaves, and we know that O delta Y would push forward to W0 intersection W1, and when we push forward this diagram, we would get another diagram, this one, and we need to do one more step. About compute the push forward of line bundles on W0 intersection W1. We could see this also by explicit computation that the image is 0. So that's by this process we could replace ER minus 1, and we can remove the O minus delta part and just replace by structure sheaf. Okay, this is the ER F minus R part, and the F minus R ER part would be a bit easier. It is it is just the push forward of the structure shift D plus, and the ER F minus R is the structure shift W0. And as I have said, that the plus have two reducible components, W0 and another component and W1. So one side corresponds to W0, and there should be another corresponding to W1. And the last part we want to show is that OZ plus, okay, OZ plus is different from OW1. They're direct sum of W1, but they are put forward to the same thing. And it also follows from this Schrodinger sequence, and we have mentioned that L1 inverse W0 intersect W1 would be pushed forward to 0. So this gives us this gives us the computation of F minus R ER equal to ER F minus R direct sum of O delta 1. And for other HK case, we could also do this. Through the same strategy, but the difference that we need to understand the push forward of line bundles on delta Y, which is Sn minus 1 and plus 1 to Sn times S. We need to give a thorough computation and understand directly about how these line bundles are pushed forward to a combination of ideal shifts on Sn times S. So this is the difference for HK and the H0 part. Yeah, so far so good. Okay, so finally, I want to make a review about what we talk right now, and we also want to briefly explain how to strengthen it to the two categorification. So first, as I have said, that we give a weak categorification, and okay, so here we should want to explain why we need some refined technique for the high order case. The reason is that we regard the EK and FL as put forward of line bundles on Z plus, but it has a requirement. It relies on a technical condition that Z plus is a Cohomology expected dimension. For the case of high rank, it is not true, because in this case W0 and W1 are not equidimensional, and we know that Cohomology schema are always equidimensional. So this would not work, and we need to find some refinement way to redefine the EK-FL and do the categorification part. And the third part, this kind of toy model for the categorical version for the dream field double of the Coha. And of course, we also expect the generation to other communicated settings. Okay, now I need to come back and explain how do we consider the two categorification. So for the two categorification, First we need EK and FK to be biased to each other, and in this case it would require that the canonical bundle surface is trivial. So I think we will focus on the case that the surface is K3 or some sense of non-compact K3, for example, like A2 or like type AD resolution. So in order to do this, we need EK and FL to be EK and FL to be biased joint. The second thing we need to do is that we want to make as for the case of breeder relation, actually we want to make a twist of EK. So we want to make a morphism of EK, for example, which we will denote as T, such as the T square would be 1. And this one could be through could be obtained through the quotient to the action on Y, because I mean look at the diagram over here. We could always change IN plus 1 to IN to IN prime and IN prime to IN. It induce the interaction on Y, and it would also induce it would also induce a morphism T, for the EK, for every K such that T square would be 1. And okay, so now we already have the operator T and the decomposition EKFL equal to FLK. Then what's left is that we need to understand the relation T with the other morphism of weak classifications, which we have introduced here by myself and also by Andrew. And we need to understand the relations of this morphism, for example, whether they satisfy some symmetric group action, or maybe there are also other unexpected relations which we have not found yet. And after doing this, we could consider how to obtain the classification from a sense of weak classification to a sense of strong classification. So yeah, so I think that's all I want to share today. And any more questions? Okay, yeah, that's all.
Yeah. Oh, sorry. Am I jumping the gun? I had a question.
Sorry. Which package? So which page?
Well, I have a question. So what is, okay, I don't understand. So the generators of this toroidal algebra, EFH.
Yes.
I would like to understand them in the type, in the case where S is A2, at least just decategorified.
Yes.
So
so do you know the Zhao algebra?